took my request to write things up seriously, right? To things it seems that we know or we have known or we should have known for a long time, but that just never got properly written up. Anyway, so take it away, Will.
Thank you. Hello. Woohoo. Just to repeat, I'm Will. Nice to meet you all. So, this talk begins with a very simple question. Where are all the functional programming design patterns, bracket closed? In fact, this question was asked 12 years ago on the Software Engineering Stack Exchange, as you can see. Specifically, this person asked, OO programming literature is full of design patterns. Most books on object-oriented programming dedicate a chapter or two to design patterns like factories and decorators. So what are the equivalent patterns in functional languages? Why hasn't anyone written a book about them yet? Is there something special about functional languages that obviates the need for design patterns? Which, I think these are all really interesting questions. They were on my mind. But you'll never guess what the top answer is. Jeremy Gibbons is writing the book. So, Jeremy?
That's a grand plan in 2012.
All right, so the book is still being written. That's okay. But in the meantime, while Jeremy's been writing the book, several other people have also decided to fill in this void. You can find now published Scala design patterns, Haskell design patterns, Scala design patterns. They're not very creative. Functional programming patterns in Scala, Scala functional programming patterns. But, okay, I have skimmed these for you, so you don't have to. And these books don't feel like they capture the essence of what made the original design patterns so influential. They tend to do one of two things. Either they translate the original design patterns into a new language, like Scala or Haskell, or they tend to explain standard library types. You know, a monad is a burrito, that sort of thing. And so to get to the heart of my question, why do I feel like these aren't really the functional successor to the design patterns? We have to ask, and I was asking myself, what is a design pattern? What is its purpose? And I'm going to give you two perspectives on this question from the old times. The first one comes from Peter Norvig, who said that design patterns are descriptions of what experienced designers know that isn't written down in the language manual. So this is an important idea. There's a term called tacit knowledge for things that experts know but they have trouble articulating. And I see the role of design patterns as articulating tacit knowledge in a shareable form. And Peter gave examples of tacit knowledge like how to choose classes and methods, abstractions for program organization, discussing design trade-offs, avoiding limitations of the implementation language. All good examples. And so this is a useful perspective, and I also want to go back to the very source. For those of you who don't know, Design Patterns is a book written in 1994 by a group of 4 computer scientists, collectively called the Gang of 4. They wrote a book called Design Patterns with the following purpose. They said their purpose is to record experience in designing object-oriented software as design patterns. Each design pattern systematically names, explains, and evaluates an important and recurring design in object-oriented systems. The goal being to capture design experience in a form that people can use effectively, so they wrap them up in a catalog. And the thing I want to emphasize is this second sentence here. Right? First, this concept of systematic naming is important. If I share all of my experience with you in a huge monograph, it's not indexable, it's not shareable in small pieces, but names give us vocabulary to talk about systems at a higher level. And additionally, this idea of important and recurring designs is really essential, because to me, what distinguishes a design pattern from something like, say, a functional Perl is it's not just an insightful or clever way to organize your code, it is something that has been repeatedly proven to be useful in real-world applications. And so to recap, I think the design pattern should, 1, capture a recurring phenomenon in real-world system design, and 2, provide a software design strategy for managing this phenomenon that is difficult to describe mechanistically. And I think these criteria can help us start to see why functional design patterns have been historically elusive. For the first criterion, it's somewhat straightforward. There just aren't that many real-world systems implemented in functional languages. Or at least the fraction of code in functional languages is dwarfed by orders of magnitude by object-oriented languages. And so we just don't have that much data. But even if we had the data, there's still a question: what kinds of phenomena are difficult to describe mechanistically? A common criticism of the Gang of Four patterns is that they arise in part due to the inexpressiveness of the implementation language, like C++. And in fact, Jeremy wrote a great paper about exactly this called Data Type Generic Programming, and there's a wonderful quote: "The origami approach to data type generic programming offers a good way of capturing precisely the essence of a number of the Gang of Four patterns. This is appealing because, without some kind of data type generic constructs, these patterns can only be expressed extra-linguistically as prose, pictures, and prototypes, rather than captured in a library, analyzed, and reused." So I think this quote gets to the heart of it, right? With a good enough static type system, or with a dynamic type system, which was what Peter Norvig was advocating, you can take ideas like a visitor and make them fully linguistic abstractions. And the abstraction itself still needs documentation, but the point is that the abstract idea behind the pattern moves from the realm of prose to code. Which, at that point, sort of begs the question, is the visitor still a design pattern if it's just a library? If we say yes, that seems to imply that any library is just full of design patterns, which kind of dilutes the term to a point of meaninglessness. And so returning to my criteria, when I ask where are all the functional programming design patterns, my thesis is that we need to do two things. First, we have to find a source of systems implemented into functional languages across a variety of domains. That's going to give us fodder to find recurring phenomena. And second, we have to revise our understanding of tacit knowledge used by expert functional programmers to build systems. When the language provides support for sophisticated abstractions, what then becomes the hard part of system design? And so in the rest of my talk, I'm going to give you my answer to these questions, but I want to put a pin in this because part of the goal of this talk is to discuss these questions, right? This being the inaugural FUNARCH, great place to talk about this. And so I encourage everyone in the audience to reflect on your own experience. What is your conception of a design pattern? What is your tacit knowledge about functional programming that you think others may not have? We'll talk about it after. But for now, I'll lay out my perspective. So to start, where can we find a large range of systems implemented in a functional language? Well, for anyone who knows me, this is an easy guess to make. It turns out there's a functional language being widely used today to design robust, high-performance systems in a ton of places. Hey, it's Rust! Okay, now some of you skeptics might be thinking, well, Rust isn't a functional language, okay? But I think it's useful to think of Rust as being functional. It's expression-oriented, it has closures, generics, first-class functions, immutability, type-level programs, and traits, which I think are the most interesting aspect of what makes Rust design distinct from object-oriented languages and similar to languages like Haskell. And so, of course, there are other functional languages we could look to with moderate industrial usage, like Clojure and Scala. I just don't know those ecosystems as well. I've been programming in Rust for about 8 years. That's my expertise. That's where I'm going to focus in this talk. Now, the second question, the second criteria, is a little trickier. What kinds of knowledge should be articulated as functional design patterns? So here's my take. In programming, you have dozens of application domains, right? You have web servers, game engines, numerics, compilers, and so on. And when statically typed object-oriented programming became popular, it offered a relatively small number of core language mechanisms with which to model the phenomena across all of these domains, especially at the time the original design patterns work was done. Everything had to be boiled down to an object. Most forms of reuse were inheritance. Code was made generic through subtype polymorphism mixed with dynamic dispatch. And the design challenge then was to do a lot with a little, to model everything with a small number of load-bearing types, which required a lot of cleverness that got articulated as design patterns. But in the FP world, it's a different story. We have so many more modeling tools at our disposal. right? You have sums, products, modules, references, lifetimes, traits, closures, you name it. And this changes the nature of design, because now you have so many tools, it can be hard to know which is appropriate for a given problem. And so I think one role for functional design patterns is to take a common phenomenon in system design, right? Something that occurs in many of these places on the left, and gives guidance on how to find a good encoding into the right subset of the many mechanisms you find down here in the bottom right. And especially when we focus on static typing, good encoding usually means things like user mistakes are caught at compile time rather than runtime. We've effectively encoded properties and invariants into the type system. And so to demonstrate that, I wrote down in the paper 4 different design patterns that I've seen in Rust. The witness, the state machine, the parallel lists, and the registry. Each design pattern describes a mapping from some domain pattern, like state machines, into a configuration of type-level mechanisms, like phantom types or modules. And I did not just make these up. Each pattern can be found in multiple widely used Rust libraries that are sourced in the paper. And now to illustrate further, I'm going to take one of these patterns, the registry, and walk you through it for the rest of the talk. You're going to learn about the specific design pattern, but again, my goal is not just to teach you about Rust. I want to argue this is representative of a way we could, in general, articulate functional design patterns. So let's get to the code. All right. So the event, again, the pattern we're going to talk about is the registry pattern. And this can be seen in a number of domains, like if you're doing dependency injection. And the case we'll talk about today is event systems. So the basic idea is you have some kind of events structure, like this, that's going to hold events. And there's going to be 2 key methods we care about. One that registers callbacks F on events. It's going to have some kind of event name, which is a string. And then it's going to have some kind of data or some kind of function, F, which is going to register that function. And then we're going to trigger callbacks given some name. So an instance of how we would use this API would be if we say let mute evs equals events default. Then we want to, for instance, register something. Register for the click event, something like println I've been clicked. And then we want to trigger this, again, with click. And that should cause some behavior to happen. We need to add a derived default up here. And I'll try to explain some of the relevant Rust syntax if it gets super gnarly. And so we can run and compile this. Right now it doesn't do anything because we haven't implemented the functionality, but we have the skeleton of our basic implementation. And so the simple way to do this is we need some kind of listeners map that's going to map, hash map, that's going to map from a string into a box_dyn listener. So a listener is the type of things that we can call as listeners. And that's represented, normally you would write out function types with arrows in most functional languages. In Rust, you have to use a trait, because that's the way you correctly abstract over things that are both raw, like plain functions and closures. And then this box_dyn thing is a way of doing dynamic dispatch. Oh, sorry, this should be a vec_dyn box. Because we want to have, if we have a heterogeneous list of many different functions, then the common thing amongst them is they implement the listener trait, and otherwise we abstract all other details. So the way we could use this is say self.listeners.entry name .or insert with vec new .push f. All right. .push box new f, putting that on the heap. And then when we trigger it, here I'll give a little more space for the type annotations. When we trigger it, we say let's get out the listeners if they exist, self.listeners.getName. And we're going to say for f in f's, call f. All right. Oh, we almost got that, except we have to declare that this is a listener. And now we run this, and our previously not working example works. It says, I've been clicked. Again, just to briefly pause, remember, the point here is this is how I think we should be illustrating design patterns, right? You sort of iteratively build up functionalities in small self-contained examples, and you need to be talking about encodings into the different types that are relevant here. And so, for instance, this is not, we have to talk about expressiveness as one dimension of these designs. This is not an expressive event system because our events do not take parameters. They need to have some kind of payload that is unique to each individual event. So the way that we'll represent that idea initially is, let's say we have a finite domain of events that we've decided ahead of time. We can represent that as an enum. So an event could be either, say, a click event, which will have an X and a Y. We could have a key press, which is, say, a char. And then a listener now takes a pointer to an event. And all of this is the same except the trigger function, where now we need to take as input some data that we pass as input to the function. And now down here, let's turn off company mode because it's getting in the way. Now down here, we're going to take as input that data and match on it. And say if we get an event that's a click, we can print that out, X and Y. And if we get anything else, that's an invariant violation. We don't expect to receive any other kind of event when registered for click. And then similarly down here, we can pass as input X is 1, Y is 2. And let's see if I managed to type everything correctly. Almost. 36. I am missing expected operator. Oh no. What is happening? Sorry. The extra semicolon. The challenges of live coding. I'm totally duffing this up right now. Sorry. Let's ask Rust to tell us something useful. Oops. I missed the thing we're matching on. See, this is the challenge, to get all the details right live, but luckily it doesn't take us too long. All right. So let's go back here. Now we've matched this, we're running it, and we've successfully executed this. And so this is decent, although it's still, obviously, you're starting to see the bones of why this particular encoding is not desirable. Because when we match on some data, there's some possibility that we might get the wrong kind of event. Or if we typo either the event names in the trigger or the register, we could send data to the wrong place. Moreover, this is also still fundamentally inexpressive on some level. It is a closed system that cannot be extended with a new event type. So an important question is, how would we make this extensible if anyone wanted to add their own kind of event? So the way we do that in Rust is essentially, first, you're going to take all of these things that were previously part of an enum and make them distinct types. So you have a struct that's a click. You have a struct that's a key press. Delete the event. And then instead of taking as input a specific type, we just say we take any type. And this is coming from the standard library. It's a trait that basically says this thing is dynamically typed. And the only change we have to make now down here is instead of matching on an event, we have to explicitly say downcast ref and then cast it to the specific type that we're expecting. And that will give us back an option, either containing the type that it is, or we get back a none if it's some distinct type. And then event 13. Oh, right. And then this also needs to change to dyn any. And type. No, you don't. All right. So now, again, we get the same functionality, but we've extended this into an extensible system. We can pass any kind of data here when we trigger the thing, and then we match on whatever data we expect to get back. So that's nice. But once again, this is still deeply troublesome because there are so many ways we could mess this up. And also, this is a ton of boilerplate to have to write every single time you do a match. But this is roughly the system design you will find in places like JavaScripts, add event listener, have something that looks like this, just fully dynamically typed, so they can hide many of these type conversions away. All right, so the core of the design pattern I'm going to communicate is how you can unify the concept of this key with the thing that it is meant to correspond to, in this case being the sort of event payload. The insight is that when we're talking about this kind of callback should only be registered for the click type, and so the type itself can represent a key. And the way we represent that idea in Rust is first we're going to need this type ID structure. And we're going to update a few of our type definitions. So instead of a listener on any, we have a listener on a specific parametric type E. We have a vector of listeners now, vector of box dyn listener of E. And then this is going to get updated to box dyn any. And the key thing is now, rather than having an event name as the key to the hash map, you have a type ID, which is the type of events that these listeners are listening on. So this is sort of it's a little bit indirect, but it's a sufficient encoding to give us the extensibility we want without having any sort of other imposition, or without having this sort of disconnect between the keys and the values. So the way that we update our type signature here is now we have some event type E that is tick static. You can ignore that part. We can get rid of the name because that no longer matters. F is a listener on E. And now when we say dot entry, rather than passing in name, we pass type ID of E. This being the key thing. The index into our hash map is the unique type of the event. We get back, then we have to do something a little fancy here. Box new, listener vec, E new. All right. Then we have to downcast that, downcast mute, listener vec, E. Because now we have this dynamically typed data that is directly referring to the vector. And then we push our function into that. Oh, and we want to unwrap that. And then now down here, when we trigger the event, again, this is now parametric over some event type, E. So we can delete the name. The data should become exactly that type that we're asking to call an event on. And now we have to, again, do some kind of downcasting. So we say fs.downcast ref listener vec of E dot unwrap. So now we've said we're specifically listening, we want a vector of listeners that are specialized to the type E. And finally, when we want to update our API, we can just start deleting stuff. We can get rid of this. We can move this click pattern match up into the type, the argument list. And then get rid of all of this. Wonderful. And we no longer need the name when we trigger this either. Now, the moment of truth, who thinks this is going to compile after everything I just typed? Oh my God. Got a name. That's right. All right, we also have to index on the type ID of E. All right, that was the only thing missing. So this is pretty cool. With this new interface, we've now unified the key, the name of the event, with the data type that it's meant to correspond to. And the nice part about that is we just have to specify somewhere in the definition of this closure what the type of the payload is, and the type system takes care of the rest. And importantly, when you're talking about communicating these design patterns, you have to articulate the things that one can no longer do, the user failure modes that now became inexpressible, which in this case are, I cannot, for instance, trigger a click callback with a key press event. So if I replace this with key press C space or something like that, then as you expect, nothing runs, and there's no sort of hack within the system to convince Rust that click and key press are the same thing. Now, of course, this is not necessarily a perfect system, and there are important trade-offs to designing things this way. Like, if I accidentally make this type weirder than I expected, for instance, if I made this sort of a reference or like an RC, and I made the types not literally unique, there are certain ways I might shoot myself in the foot and then not realize that I was registering an event for a different type than I expected. So you still have to be a little bit careful, and it's possible that you might sort of register something for the wrong type and then just never have your event get called, but you'll never have these sorts of invariant violation failures. That's the promise of the registry pattern within Rust. And again, there's a similar idea where if you use dependency injection and you ask for specific types, you can make sure you only get correct values of those types. And you can see there's actually several different implementations of this kind of pattern within the Rust world. So let's bring back up the slides. There's my tweet. And then I think, there we go. Right, to emphasize that this is a pattern, you can find a version of this in the Matrix client, which is a chat server that uses these extensible event contexts. You have the liquid string templating language, a version of that written for Rust, that uses a plugin mechanism where you can add arbitrary features to the language using this construct. And then when you have games like Bevy written in the entity component system architecture, they use a similar kind of idea to have this global map of like global mutable state for the game. And you can say, I'm going to get global mutable data of this type or global mutable data of this type. And you can fetch those independently of each other from this central store, which has almost an identical hash map structure. All right. So that's pretty much what I wanted to say. Again, the high-level idea is, what is a functional programming design pattern? I hope I've given you some food for thought on the principles that should guide that, that idea of coming up with a definition of a design pattern. I've shown you one specific instance of what a design pattern could be in the context of Rust. And finally, I want to wrap up by having a great discussion about all this. So here's the way I actually want to structure this, especially because there's a lot of you, is I'd like everybody to find your 5 closest friends, and we'll do a little roundtable small group discussion, and then you can all ask me or tell me something interesting that you discussed in your groups. So here are some great questions to get you started. Of course, you can talk about anything. Like, what are the qualities of a good functional design pattern? Or do you have specific good examples that you like? And if we were to truly construct the successor to the Gang of Four's design patterns for the functional era, how should we do it? What are the elements of that construction process that should be considered? How do we find these good examples? So that's my talk. Let's get discussing. Thank you. So let's take, I have 15 minutes, I believe. Yep, so let's take 8 of those minutes to do small group discussions. So again, just find your 5 closest friends. Talk about these questions with them. And then you can, I'll be there, and we can talk at the end. Go for it. All right, everyone. Let me get your attention for 1 second. This is amazing discussion, and I love it. We have 2 minutes remaining until we have to swap to the big group. So what I want you all to do is pick one person who will share one thing. It's either a comment of something interesting that you want to just share with the group, or a question. You can ask me, and I will respond. So 2 minutes. Figure out what you're going to say. Go for it. Is this working? All right, all right. Everybody bring it back. Everybody bring it back. Focus, focus. We're now returning to the collective unconscious, the group mind. That's where we're all at now. So, who would like to volunteer to offer a cool fact or question? Thank you.
We think that in Haskell, at least, we already have design patterns in form of type classes in base, like traversable, like monoids, semi-group. They're used all around. State monad is also like this. They form your code. They're used everywhere.
Yes.
And enforced statically. It's similar, for example, you have observable design pattern. It's on the same level of abstraction, like traversable, for example. It's similar, like a level of abstraction. That's our comment.
Amazing. Thank you. Yeah, that's a great point. And I think this is an important question. When is an abstraction a design pattern, and when is it not? You know, because again, I will just comment on that. You know, my sense is I think we should not consider those abstractions to be design patterns in like a, you know, you can get definitional about this in a way that's not useful, but I think the point I'm trying to make is we should redefine design patterns to be the kinds of knowledge that cannot be encoded as those things. Like once we have something that's a fully linguistic abstraction like that, that's great. Now we have an abstraction. And design pattern is now everything that's left. That's how I would say it. But I think these are both totally correct viewpoints and consistent with how people use the phrase in practice. So I think that's an interesting tension. Hans, yes, please.
So John Vlasidis was right with you. I wrangled with him many years ago, and he told me if it could be formalized, it's not a design pattern.
Okay.
So we have a lot of questions. What's the difference between a design pattern and a tip or a trick? So we came up with a couple of tips and tricks, like write combinator libraries, or if your problem has a sequential composition, consider writing code that uses function composition. Are these design patterns, or are this just things that experienced designers know that are in the manual? We don't know. Right.
Yeah, great question, or great point. You know, and to me, I feel like there's something about a pattern that evokes the notion of a template. There's something of, and this is something I bring out in the paper, and I don't talk as much here, is that there are distinct like abstract elements. So in the concept of the registry, you have like the key and then the requests that are keyed on that key. And you can identify in every instance of the pattern, whether it's event systems or dependency injections, a mapping from the abstract variables, abstract sort of schematic pattern variables into the concrete instantiations. And that to me has the essence of a pattern. And whether that captures the examples you're proposing, I'd have to think about, but my thoughts. All right, in the back.
So I thought that was a really interesting and eloquent way to put it. If it can be formalized, it's not a design pattern. And one thing we were talking about is if we were to forget all the knowledge we currently have of design patterns, would the same ones reemerge later? Like, are design patterns discovered or invented, essentially? Yeah. And I think if they reemerge later, they're probably more formal, like the applicative laws or something like that. But it's not necessarily the case that we would rediscover the flyweight pattern or something, unless we happen to run into the right conditions.
Yeah, great point. You want to mention? Yeah, go ahead.
Yeah, I think we discussed. I think there's one, just like Sean mentioned. There's one thing actually quite common in the industrial settings. Really like we actually do a lot of large-scale data transformations. So you kind of like really design a data pipeline from just like a different paths in compiler. You really have transformed this data from multiple stages, and that's actually quite a common higher-level architecture pattern, I would say. And it is not particularly articulate, but I see a lot. I've seen a lot. So it's kind of like, oh, that's one thing. The other kind of we can discuss really like, because in my company, I'm doing their basically static analysis. When we use some different tools, if I use under C++ code, I use clan. Obviously, I'm going to use the AST represented in the object-oriented type hierarchy. Then you're going to use the visit pattern to do this thing. And that's a standard design pattern in OOP world.
Yeah.
But if I use functional programming, then I use expressing ADT, then it's pattern matching, which is very straightforward. And do we call this design pattern? This is obviously a language feature, a very prominent language feature in functional programming language. Right.
Right.
And it's really like in OOP language, you cannot, or you have to represent your object syntax tree or algebraic data type via OOP design.
Yes.
Then you have to have this visit pattern to achieve the pattern matching.
Yeah.
Right. So that's kind of like, yeah.
Right. Yeah, no, fabulous points. And I think this issue also of granularity is super interesting because both the original design patterns and the ones I'm talking about are sort of like very fine-grained code and distinct from like the hexagonal architecture, these sorts of things we've discussed.
Hi, thanks for provoking us, Will. I'm going to agree and disagree with John Vlasides. So if it can be formalized, it's not a pattern. Fine, that's good. But if it can be formalized, then that's not all of the pattern. What you formalized is the formal bit of the pattern, and the pattern is all the tacit knowledge that goes along with that.
Right.
And that was the obstacle I had when I tried to sell this data type generic programming thing as this is what patterns are to the OO people, and they said, no, it's not. We've missed out all the other stuff, which I think is fair enough. So traversables was mentioned. The paper by Conor McBride and Ross Patterson that introduces this is great because it does the formalization. It says, here's the construction. It doesn't leave it there. It goes through and explains a whole bunch of applications of it and things that you might not have noticed the first time you see the piece of code. So that's unpacking the tacit knowledge that they had, perhaps if you like, and making it explicit. So and that's a great paper, and I think I've come to think that the functional programming equivalent of design patterns is papers like Functional Pearls. They capture a lesson, a fact. It might not be a new fact, and the fact that's taken as a point of honor in the design patterns community. You don't invent patterns. You have to mine them from existing stuff, otherwise you're just fabricating things. It doesn't count. So fine, doesn't have to be a new idea, but giving it a name so that people can use it, and telling the story around it so that people remember it and can see how it will fit into their context. That's all part of the pattern. And I think our way of expressing these and recording these is things like functional pearls.
Yeah.
So what are the qualities of a good functional design pattern? I think they pretty much coincide with the qualities of a good functional Perl.
Okay. Well, it's a great perspective to end with, because I think we're out of time. We'll move on to the next one. So thank you all again for your wonderful comments, and I hope this is thought-provoking beyond this session. We can continue to talk about this.